So in today's lecture, I'm going to discuss about the descent function, and this is an important concept in constraint optimization, which we can use to monitor the progress of the constraint optimization method. And this is lecture 35, and I'm Dr. Ranjan Ganguly. Now we have seen that in typical unconstrained optimization problem, the cost function lets you track the progress of the method as the method moves towards the minimum point. So as you progress from case 0, 1, 2, and so on, you can look at the cost function and see how it is progressing. In contrast, if you are dealing with a constraint optimization problem, you need to create a new function, and this is known as a descent function, to check the progress of the method. And this is because your cost function may be decreasing, but you may have violated a constraint, in which case you are not doing particularly well. So therefore, what the descent function does is that it adds a penalty to the value of the cost function because of the violation of a constraint. And so this is a direct extension of the concept of penalty methods. And now that you are familiar with penalty method, it will be quite easy to understand this concept of a descent function. Now the descent function should have certain features. One of the features should be that the value at the minimum point should be the same as the cost function, because naturally when you are at the minimum point, the constraints will be satisfied, and therefore the descent function value will become same as the cost function value, and the penalty term should become 0. Now to develop this descent function, we start with the Lagrange function. So if you recall from some of the first few lectures when we were developing the KKT conditions, the Karush-Kuhn-Tucker conditions, we had defined the Lagrange function as a composite function which contains the cost function f of x, the constraints hx equal to zeros, and the constraints gx less than equal to zeros. And vi and ui were the Lagrange multipliers for both these type of constraints. So we will start with this particular Lagrange function and then try to simplify it to a form which is usable. So if you recall from that definition of the Lagrange function, the vi Lagrange multipliers are free in sign and the ui are greater than equal to 0. So this is something we know from our previous studies as far as the derivation of the necessary conditions for a constraint optimization problem. Now what we are going to do is we are going to try to find a bound which can be used in some practical problems. So once again, let us look at this L of x, and now we can see that this L of x would be less than this function here, because what we have done here is taken the absolute value of vi hi. Now remember that vi is free in sign, hi is also positive or negative depending upon the degree of constraint violation, and therefore this term could be positive or negative, and so some cancellations may take place. But if we take the modulus or absolute value, then this function here would be greater than the function here you see on the top. Now proceeding on the same path, let us suppose there is a value v of x which defines the maximum level of violation of a constraint. So this could be the maximum violation between h and g, and so if we were to extract such a function outside from these summation signs, then we could write both these summations inside this bracket here, and so you would have the modulus of vi, you would have ui being greater than equal to 0, the whole thing in brackets, and then you would have some function v of x which at this point is not known. So therefore we can finally write the expression Lx is less than equal to this function f of x plus rvx, and we will call this composite function as phi of x, which is the Pschenichny descent function. So this expression tells you that the Lagrange function is a lower bound on the Pschenichny descent function, which you can see here. So Lx is less than equal to phi of x. Now let us look at some of the terms which were there in that descent function. So the first term was r is greater than 0, and that is a penalty parameter, and it is essentially defined as follows. So if we have a substantially large value of r, then it would be a value which would satisfy this particular expression. V of x is a penalty function, and so it can be defined as follows here. So here you can see that this is going to be the maximum violation of the constraints. Now there are three possibilities. Of course, if you are in the feasible region, all the constraints are not violated, and so V of x would be 0. If a h constraint is violated, you take the maximum value of that and you take the mod here. So this would ensure that whether you are negative or positive, both situations are taken care of in terms of violation. And of course, as far as the g constraints are considered, when they are violated, they are greater than 0. So again, in those situations, you would take the maximum value here for the constraint. So essentially, V of x would be the maximum violation of a constraint. Now at point xk, the descent function is given by this expression here. So here you have the function value xk at xk, which is f of xk. You have the penalty parameter r, and you have the penalty function value v of xk. So this is your composite descent function, or the Pschenichny descent function. Now the Pschenichny descent function is something we are going to use later in our studies on constraint optimization. So this is a point where we just introduce that particular concept. Now there is one more concept which is very important in constraint optimization. And this is important because in general, when we mathematically think of a constraint being satisfied, we think of an equation or an expression of the form gi xk is less than 0. But typically, when you are dealing with a computer program, you are at some boundary of the feasible region. So let us say we specify some small number epsilon here. And so this particular constraint gix less than 0 is epsilon active at a point xk if the following two conditions hold. That means gixk plus this small number is greater than or equal to 0, so there is a violation, but gixk is less than 0. So here epsilon is greater than 0 is a small number, could be 10 to the power minus 4, 10 to the power minus 8, depending on the degree of precision you want. And what this is telling you is the point xk is close to the constraint boundary, and how close it is to the constraint boundary, because this is something we now want to quantify. And the reason is that because at the particular point where this constraint becomes active, it will become equal to 0. And that is actually often not a very good design point. And also there is going to be certain point here where this constraint is actually violated, but to a very small amount. So again, these are some subtle facts about constraint violations which often become important, because you are often dealing with computers which have finite precision, and therefore you never get a situation where gix is actually equal to 0. You are close to constraint violation, or you have just violated the constraint. So you are in this particular boundary of the feasible region as far as typical numerical optimization is concerned, and that is why this particular concept becomes useful. So again, these were some concepts today which will help us further grasp the situation in some of the constraint optimization methods. And in the next lecture, we are going to look at sequential linear programming. So this culminates lecture 35. I will see you in my next lecture.